Thank you very much. It's great to be here today. I'm going to talk about something quite different today. I'm going to talk about how we leverage Scala to build hardware at scale at SiFive. So by now, you're wondering, what do I mean by hardware? Which part of the hardware am I talking about? So today, we're going to talk about how we leverage Scala to build chips like that, the microprocessors or system on chips or SoCs. Personally, I really don't like the word SoC, but that's what the hardware industry calls them. So SoCs, SoCs, chips, microprocessors, all interchangeable during the talk. So before I talk about that, I'd like to talk a little bit about some trends in the hardware industry. So, the first trend that I see is compute needs are changing. Our imagination is endless, it's limitless. We keep coming up with all these workloads that are computationally demanding, like machine learning. We talked a lot about that here today at the conference. But we all notice that CPUs are not getting any faster. This is the spec-int score compared to the VAX11 back in the 1980s, and you kind of see that it started stagnating at 2015. When was the last time you bought a computer that was blazingly faster than the previous one? So people have been doing a lot of things to overcome those problems. First, we talk a lot about how we're accelerating the workloads on GPUs. GPU is a custom piece of hardware that is more specialized for certain applications. Some people go all the way to building custom chips. Like Google TPU is a great example. It excels at doing one thing very, very well, but it doesn't do quite well on other things. That's all good, but what's the problem? Custom chips are very, very expensive to develop. So this is the process technology node. As you go to the right, it's more modern process technology node, like 16 nanometer and 14 nanometer. And developing a chip on that process node takes about, according to this graph, $320 million. This is an exponential gap where there are more compute needs that are rising. CPUs are not getting any faster. We need more custom chips, but less and less people can afford it, right? This is a huge problem. So I've been telling my colleagues in hardware that we have to just blatantly copy success from the software world. And I think there are 4 things about it why software world excels. And the 4 things are open source, abstraction, composability, and productivity. Open source is the ultimate form of reuse. The best way to build your application is to not write new code. Just go leverage all the code that's out there. I mean, that's the best way of building applications. And open source is the ultimate form of sharing. Abstraction is a great way to split your important interfaces to the implementation so that whenever a new thing comes along, you can quickly adapt. Composability is how you compose all these important interfaces to build a bigger system quickly. Last but not least, productivity is that obsession about tools on how I'm going to do less and less stuff and be lazy about it so that I can do more and more things with less effort and less people. There's 4 things. So the sad thing is, every time I go tell my hardware colleague about this, everyone says, we're doing this too. So then I have to tell them a story, right? So Instagram, right? Then they say, yes, I do know that. Do you know they were $1 billion when they were sold when there were only 13 people? And they're like, whoa, that's $80 million per engineer. Wow, that's great. And then I have to remind them, why does a hardware startup, just to get started, you need at least 14 engineers to get started? And they're like, oh yeah, that's right. 14 engineers off the bat, forget about the $1 billion, valuation or something. This is, by the way, I counted them, and I got really depressed and really jealous about the software industry, by the way. So after that period, I kind of started thinking about this. So why is that the case? So if you go Google Instagram tech stack, actually the software world just shares all the technology that they use. There's 2 things: ease of development, ease of deployment. Nobody in their sane mind today goes and builds Linux from scratch just to go build a web app. Nobody goes and builds these databases from scratch. Nobody does that. You just go download some package and you get going. And couple that with ease of deployment. You don't need to go build a data center to go build a web app. You just go buy some compute. And as a matter of fact, Amazon gives you free compute at the beginning to kind of lock you in. So you just can get started. And couple these two things together, you can quickly iterate. You can deploy your application, get feedback, fix the things that don't work, and then you get a billion-dollar company at the end of the day. So, by the way, hardware doesn't look anything like this. So that's what SiFive is trying to do. SiFive, we're building a tech stack, hardware tech stack, based on open source technology. Not sure how many of you guys heard about RISC-V, but this is a free and open instruction set architecture that I started working when I was a grad student at Berkeley. As a matter of fact, we were the upper story of the AMP lab who did the Spark. And that's why we got into Scala. So on top of RISC-V, we build Chisel, which is our hardware construction language built in Scala, and FIRRTL compiler, which takes these circuits down to industry standard circuit exchange formats like Verilog. And of course, we leverage Scala, and hence the reason why I'm here today. It's really hard to find people who intersect between Scala and hardware, and this is my Hail Mary to go find some people. So we're interested. So that's all the open source technology, but even though you have all the hardware components that you need to go build a chip, building a chip still is $300 million. So that's the part SiFive is doing. We're building a web service to help you go build hardware. So I'll talk a little bit about that today too. But why? Why are we building all this open source hardware stack? Why? Why would you do that? So this is the initial team at Berkeley who are doing RISC-V. If you count all these people, it's about 12 people. So with 12 people, what we did is we defined a new instruction set architecture. We did the architecture, we did the marker architecture, we did all the porting of GCC operating system, build a chip, package it, test it, get it on the board, and actually do it. We didn't have an army of engineers when I was at Berkeley. A lot of these companies have 1,000 people working on one chip. We didn't have 1,000 people, so we had to do something differently. And with a dozen people, we actually built about 18 chips for the past 6 years, actually. 16 nanometer chip. It didn't take $300 million. We did it quite, I guess there is some sweat from the graduate students too, but there's a lot that we got from Scala too. So it's a combination of two things, But nonetheless, Scala was a big part of the entire thing. So quick introduction on RISC-V. It's a free and open instruction set architecture. So what is an ISA? It's the language of a microprocessor. All the software that we write has to boil down to these set of instructions. So the ones that are popular today are x86 and ARM, which are all proprietary. So there's really nothing we can do about it. So RISC-V is a free and open version of it. So you can think of it like Linux of ISAs. So it's a 5th generation of RISC design. RISC stands for Reduced Instruction Set Computing from UC Berkeley. Andrew, my colleague and friend, and I started the project in 2010. These are the 4 RISC projects that were there before. And we're experiencing a rapid uptake, both in industry and academia. And ISA is designed for the smallest microcontroller all the way up to the biggest supercomputer. And since RISC-V is a free and open standard, there are open source implementations of the ISA, but there's also proprietary implementations of the ISA as well. And it's supported by a growing software ecosystem. All the GNU toolchain stuff, binutils, GCC, newlib, glibc are all upstreamed in their respective projects. We have a bunch of operating systems ported like Zephyr, Linux, FreeBSD, and a bunch of distros ported to RISC-V like Fedora and Debian. And the standard is maintained by the nonprofit RISC-V Foundation. So if you want to make any additions or suggestions to the ISA, you can join the foundation and you can suggest changes to it. So the RISC-V Foundation members consist of about 125 plus companies. You see a lot of the giants there. If your company's name, logo is here, thank you very much. If you're not, maybe consider joining. It's a lot of cool stuff happening there. So to show you the state of the software for RISC-V, I pulled a graph from the Debian webpage. You see that hockey stick there? That's the number of RISC-V packages ported. And that has been done in the past 3 months. We went from 0 to 80% of Debian packages ported to RISC-V. And I'm happy to report that we have more packages ported than IA64. Itanium, that's it's not being used today, so. So when there's a new thing, a very important thing is education too. So I'm also happy to report that the undergraduate textbook and the graduate textbook for computer architecture written by Dave Patterson and John Hennessy have all adopted RISC-V. So all the undergraduates and graduate students who are coming out of school will be up to speed on RISC-V. Okay, I'm going to switch gears a little bit and talk a little bit about the hardware that we built at SiFive. So this is FU 540, Freedom Unleashed 540. It's a 64-bit multi-core RISC-V SoC. So all the chips have this block diagram associated to it to kind of specify what's on the chip. So in the heart of the chip, you can see the U54MC core complex. It's a multi-core, 4-core, quad-core, 64-bit RISC-V application processor with an L2 cache and a DRAM controller connected to it. There's a bunch of peripherals like SD card reader, SPI, I2C, UART, GPIO, and all that. There's a gigabit Ethernet, and the guts of the chip, which is called TileLink, is also coming out of the chip so that you can connect FPGA chips, which is good for prototyping hardware. So you can map your custom hardware in the FPGA, and you can connect it with the chip, and you can actually write software for it so that you can kind of prototype your hardware before you're interested. So this core runs at 1.5 gigahertz. It's manufactured in TSMC 28 nanometer. We also put this on a development board with 8 gigabytes of DRAM, and it's fully functional. We also built an expansion board where the guts of the chip is coming out, so it's connected to this FPGA, so that you can pour your custom hardware into it. And this FPGA has a PCIe connection over here, which there's 2 slots to it. So there's a by 16 PCIe slot and a by 1 PCIe slot. So you can connect in a GPU card here and a USB card over here, and there's an NVMe drive on the back. So it's a real machine. So it runs Debian, webcam, tweets. We're at Twitter today, so. Tux cart on the back, all works. And so this one is running YOLO v3 on NVDLA, which NVIDIA has open sourced recently for their edge inference machine learning accelerator. So we map that onto the FPGA, and we connect it with the RISC-V board, and all the drivers and all that is ported to it, and you can run these type of things. So I like to show you a demo of the board. But the cool thing is you've been seeing the demo already. This entire presentation was running on the board. So Google presentation, and the web browser and all that works. Wait, I'm waiting for an applause. I'll prove this to you, right? So it's JavaScript JIT is not there yet, so it's maybe somebody can work on it. So here's the terminal. It says RISC-V 64. See, if you cat the proc CPU info, you can see it's RV64 IMAFDC, and it's SiFive and the Rocket processor right here. So it's a 4-core machine, and it's Debian. So the standard software thing just works. So I'm going to go back into presenter mode. It's kind of cool, I think. All right. Okay, so how do we build this? So that was all the marketing speak. So let's go see some code. So before I tell you all the Scala stuff, unfortunately you have to understand a little bit about what it takes to go build a chip to appreciate what's going on. So the traditional approach of building chips, at the lowest level, there is something called GDS2. That's the blueprint of the chip. It has to be manufactured in layers. It's like building a cake. It's a 48-layer cake, and you kind of shine light, and you take some parts off, and it's like building a building, right? So that blueprint looks like this. And in this, there's all the transistors that are designed into it. And the reason why the $340 million thing is $340 million is because it typically puts like 20 billion transistors together. That's kind of crazy. So back in the day when Intel were building 386 and 486, people drew this like by hand. These are polygons, and you call that polygon pushing. And there's all these rules that you can't put this thing next to this thing, and all that. It's almost like building a pyramid. You kind of like you can't take it in. It's crazy, but people did that. Like some people still do that. So people in the early 2000s, people were like, yeah, that's too much. There's something called languages, and you can compile things and things like that. So I briefly mentioned Verilog to you, right? So there's Verilog there, and this is a language. So there's some state elements. It's a counter, which only counts when the enable bit is high. You can see the counter updates, and otherwise you leave the counter. And when you reset, when the reset line is high, the counter gets initialized to 0. So this is better than pushing polygons. But this Verilog language, initially was developed for verification, not hardware construction. So there's all these language parts that are not synthesizable. So it's like somebody has to look into the code and tell you like you can't do that. Like it's not a great language to build hardware because there's all these things you can do wrong. Like why do we have a language like that? So please.
I'm sorry. Does Verilog describe the layout of the chip or the?
I'm sorry. This is the functionality of the chip. You have to synthesize into gates, and there's a tool called the place and route tool, which takes the gates and sprinkles it around with knowing the design rules. So that's automated now, parts of it. So the entire industry has successfully raised the level of abstraction, for sure. That took 20 years, and it was great. It was very successful. But if you look at software, it's like I draw analogies here. GDS2 is binary, like your exe file, your L file that you have to run. Some people can write binary into like your text editor, and you can write a working program for sure. I mean, I used to do that in PC tools in the DOS days, but some people can do that. But going and touching up the GDS2 is basically that, and you're thinking like, why would you do that? Then there's this assembly language which raises the level of abstraction a little bit more, where you still have registers and all that, but still it's not composable and it's hard to maintain. I think Verilog is that. And the software world basically figured out a way to raise the abstraction even further, like compiled languages, like high-level languages, and even Scala, which compiles onto the JVM and all that. And some people don't want to program Scala. Like, give me a web application. So you can go even higher than that, so that you can kind of hide all that and deliver value still. So this is what we're doing at SiFive. We're not stopping at Verilog. We raise the level of abstraction to something called Chisel. It's our language that we use, which is embedded in Scala. And we use a compiler infrastructure called FIRRTL, which basically turns the circuit into a compiler problem, which FIRRTL is also written in Scala. And for some people, that's a little bit too much still, so at SiFive, we're also building web services on top of all of this so that we can even hide all the Scala-ness of our infrastructure. So that's what we're doing at SiFive. So let's dive into Chisel first. Chisel is a hardware construction language embedded in Scala, and there's a reason why I said that, not HDL, which means for hardware design language. In Chisel, we strictly have only things that you can do which are correct to go build hardware. So we removed all the things that are illegal in the language. Chisel is basically basic hardware building blocks in classes in a Scala abstraction, like registers, fluxes, and wires. And we're using the modern programming language to productively put them together. That's it. Using parameterized types, object-oriented programming, functional programming, and we leverage static typing, which are all functions of a modern programming language, and it's great. So with all this, we're basically doing meta-programming for hardware, and the nice thing about this is the meta-programming language and the construction language are in the same language. And since it's embedded in Scala, one of the core values of Scala is to let other people build higher level abstractions on top of the language. Chisel is embedded in Scala, and we let people do that on top of Chisel as well. So, as I promised, here's some code. This is a ripple carry adder for those who took a digital design class. You all remember how to build an adder. It's a 4-bit adder here. It consists of 4 1-bit adders. All the inputs for each bits go in, and the carry, kind of crosses along, and your sum comes out. So this is Chisel code. As you can see, it looks Scala-y. There are things that are defined by the Chisel 3 package, like module, input, bundle, I/O, uint, wires, and things like that. And we overloaded this : equals function on these modules to facilitate something like a domain-specific language. So this, is all instantiating 4 adders, and you declare wires in between, and you connect them with a for loop. So the act of executing the code will have a data structure of the circuit in the memory, which we serialize down to Verilog. So this is how Chisel works. But you probably are looking at this code, and you're like, this doesn't look like Scala. And we acknowledge that. Like a lot of the people who come from the Verilog land, this would be the first code that they would write in Scala and in Chisel, and they'd be like, yes, I use a for loop, and that's great. So there's multiple ways of writing this, and slightly generalizing and parameterizing it and making it more, more Scala-y. So I've generalized this into a prefix sum, which we know that there's a list of things, and the output of the thing is you do the operation on all the things. And so, for example, if you had an integer adder for all the summons, this would be the output. Output 0 would be summon 0, output 1 would be 0 plus 1, 0 plus 1 plus 2. So generally speaking, this prefix sum definition would look like this. You give a sequence of summons, and you give an associative operation, which operates on these types. Great. So here's a concrete implementation of the prefix sum, which I'm calling the ripple prefix sum, which basically implements this structure over here. You do this operation, and then you call a recursive function to write all the layers down. Note, I have not used a Chisel type yet. It's parameterized types, T. Right? So you can actually give a Scala type to it, and it will just work fine. A slightly more complicated version, which is faster with less layers, is doing this parallel prefix sum, or dense prefix sum, where the first stage you do it with the offset of 1, you apply the operators. The next stage you do operator for every two lines over here. The next one will be 4, and then you stop when the offset is larger than the length of your list. So here's the dense prefix sum implementation. You shift the offset by 1 every stage, and you do the associative operation, and then you just call it recursively, and you're done. And you can use all this to go implement the adder that I just showed you. So note, I didn't really have any Chisel types now, so I'm going to make it a bit more concrete now with the actual Chisel types. So this example will basically select the first valid data element off of this list of valid IOs. Also is still parameterized. So valid IO brings a valid signal and the bits, the payload of it. And basically, I want to examine all the valid bits and only return the first valid element is a circuit that I'm building here. So, I provide the method of the prefix sum that I want to do. In this case, it defaults to dense prefix sum. Then I register all the data, and then I call the prefix sum with an operator that operates on the Chisel data type, and with all the valids, and I basically shift that, and I find the first valid one, and I put that through a mux. So I didn't have time to draw this pretty, so this is my handwriting here. So assuming that you have 4 elements over here, the valid types come in. Here's the registers of all the valids, and here's my dense prefix sum with the OR operators. And with all that, I shift it down, and I flip the bits and AND it so that I get one hot signal over here. Then I can put it into a mux, and I'll get the first one. So that's how we use Scala to go build cool hardware. And the output of that is this, the in-memory data structure of the circuit, and this is the IR, an intermediate representation of a circuit. So, and we call that FIRRTL, flexible IR for RTL. So what happens is there's a front end, which is basically Chisel. Chisel executes, and it generates a FIRRTL, internal data structure. And then we push it through a bunch of transformations to get it down to something that we can emit into a Verilog format. So if you look at that, it looks like a traditional compiler where you can put a bunch of transformations of your own when you're transforming the circuit into some Verilog. So at a high level, it looks something like this, similar to what software world does, where there's a bunch of projects and a bunch of libraries, which are written against this particular language. There's a front end which breaks it down to IR, like LLVM IR, and then you do a bunch of transformations, and when you're done to emit code, you will map it onto a backend like x86, ARM, or RISC-V. So similar to that, we have a bunch of projects that are going on. So Rocketchip is the processor library written in Chisel, which, by the way, I searched GitHub today. All the trending Scala project, it was number 25 on GitHub, so that's kind of cool. There's other library like Chisel utils and things like that. So rather than just wrapping all this around in Chisel and implementation, what we do is we have a front end. We have a language, it's Chisel. And we have a Chisel front end, similar to Clang, which turns into FIRRTL, and there's a bunch of transformations that run, and at the end of the day, it will map into a certain backend, which today it's Verilog. So, and all the FIRRTL infrastructure is also written in Scala. So to give you an example, here's how a transformation would look like. So this is a pass, which runs on a circuit, and for every module that I match, I'm going to call the squash empty, util function. So this is a very simple example, but you can see a lot of the things you could do, which are orthogonal to your program. The circuit. So, so those are kind of the important things that we use to build hardware, Chisel and FIRRTL, which are all in Scala. And I'd like to kind of show you the web application layer that I just talked to you about. So for folks who want to design RISC-V cores who don't want to deal with a Scala program, you can just come to our website. It's called the Core Designer. And there's all these kind of functionality and optionality that you can go configure. And then you can go review and build. And this deploys to Microsoft Azure Cloud, where we have all the right tools. And it compiles Scala. It runs all the tests before there's a delivery ready for you. So that's what we do for Core Designer. And we're not stopping there, by the way. This is SiFive Chip Designer, which is building your own custom chip. So you can load some templates with certain blocks, IP. I know this is a foreign word. It's called intellectual property. It's a block that you have to pay money to get. So I call it IP blocks. So there's a bunch of IP blocks that you need on a chip. So there's a bunch of third-party vendors that we work with to onboard their IP blocks onto our platform, so that once you want to go come build a chip, you can come to this website and you can select your bits and pieces and do some configuration, and you hit review and build, and we will take care of the rest of all the things that you've seen. Synthesis, place and route, making sure the design rules are met, manufacturing, testing, packaging, and we'll give you a working die back to you. So we're building this with a bunch of partners in the industry. So we're building this entire stack and we're integrating all that into a web application. So I have to tell this, thank you very much for working on Scala. It's really important to us. We bet the entire company on Scala, as a matter of fact. And, but the thing is, it's really hard to find people who know Scala and hardware at the same time. If you know Scala, more, and if you think this is cool, hardware is simple. Believe me. We can work on that. So, please come work at SiFive, join the revolution, and thank you very much. I'm happy to answer any questions. That's right.
You can showcase it.
Absolutely.
But any practical applications that people did using this, you can talk about.
Right. So Western Digital has announced that Martin Fink, the CTO of Western Digital, has announced that they plan to move all the billion cores that they're using to RISC-V. NVIDIA has already announced that all the microcontrollers that go into their GPUs will be all RISC-V. So that was about 1.5 years ago. So I don't know exactly, but my suspicion is the GPUs that are coming out today will probably have RISC-V processors in them. So the particular customers that we work with who have already announced their product is Huami has a smartwatch which has our microcontroller in it. There's a company called Fadu who builds SSD controllers with it and NVMe drives and things like that. So and there's a bunch of projects that are happening all over the world. So which probably will come out soon.
So 2 questions. The first one is not really clear why exactly Scala, because it seems that you don't reuse compilers after web authentication. The first one. And the second one, if this Scala code translates to something that doesn't make any sense in hardware, will you cache it on the stage of compilation, or will you do some tests after that?
Right, so the first question is why Scala? I don't really see a good reason why you're using Scala. The second question is, sorry, I was thinking of the first question. I'll answer the first question, I'll re-ask the second question. So we started out with Ruby when we were doing all this. Oh wow, this was a forbidden word here. And then, we were talking to the folks downstairs who were Ant Lab guys who are doing Spark at the moment, and they basically sold us on Scala. They're like, why are you using Ruby? Scala comes with a great runtime. It's statically typed. There's the way that the syntax works encourages good-looking DSLs. So, I mean, it looked great, and I'm not regretting that choice at all. The actual benefits of using Scala doesn't come from the leaf level modules, actually. There's a lot of programmability that goes in when you're interconnecting the entire thing, because a lot of things change when you interconnect. And we basically built a Scala framework to go deal with all that. And it was probably impossible to do with any other language, maybe, I don't know. The second one I remember now is, do we cache the output of the generated hardware?
Do you catch the errors on the stage of compiler?
Right. Do we cache any errors? Yes, because Scala, again, is a statically typed language. There's a lot of bugs that we don't even see before we go into elaboration. There are obviously errors in the microarchitecture hardware design itself, which we cannot really debug in Scala. But I think there are ways to go do that, and we're certainly open to exploring those possibilities.
Great question.
What's next for SiFive in terms of capabilities that you want to give to customers or where you want to expand?
What's next for SiFive is the question. So the reason why I started SiFive is when I was at Berkeley, I felt extremely lucky to be there because we had free tools and we had free, space to go tape out chips. And with that, I was enough to be dangerous enough to go build my own processor and compilers and all that. And it was a blast. I knew nothing about building hardware before I came in. I actually was a software person who wanted to know more about hardware. And I felt extremely lucky that I got a chance to go do that. But if you look at hardware today, since it's $320 million, there's only certain places around the world where you can learn how to do that. I think that's bad for the hardware industry. And the numbers actually back that. The hardware industry is only a $400 billion industry when the software industry is a $1 trillion industry. There needs to be more developers. And when was the last time you met somebody from undergrad who was so passionate about hardware? It hasn't been a long time. It has been a long time. Yeah, so the ultimate thing for SiFive is to build this open source hardware development ecosystem where a lot of the people will use Scala to go build hardware. And it turns out the new people who hasn't really learned Verilog and things like that, they have an easier time building hardware with Scala, it turns out. So I think there's a lot of things we can do there. And my final goal is so that anyone in their world, 2 people who are determined in their garages, can go build a chip startup. That's really what SiFive is going. Thank you for the question.
How do you think about integrating Chisel into overall system vendor groups? When I talk to hardware teams,
Yes.
They usually say, okay, we tried Chisel, it's interesting. However, when we run simulation, we see all these million wires which are only underscore U.
Oh, you're quite familiar with the process. Right, so the question was, how are we dealing with the ecosystem with Chisel, because the output looks very different. So every time somebody comes to me and talks about, named wires with T underscore and U underscore things, I ask them, when you debug your software, do you look at assembly code? And some people do, yes, sorry. I do too, I'm not trying to offend you or something. But most of the time, you can use high-level debuggers and other type of tools to go debug your software. And as you said, that's some of the problems of Chisel, which is a new language where certain ecosystem things are not there, which will help you debug all these things. So I showed you the whole stack of partners that we're working with. And since Chisel is getting some traction in the industry, some of the commercial vendors have started to wonder what they should be doing about Chisel and Chisel-generated code. That said, I think we're not there yet, but I think with more and more people using the language and using all the existing libraries and having like an ecosystem and a development network, and I think we'll get there. I think we'll get there. So the question is, what type of customers SiFive have and what are they working on with us? It's a great question. So Chisel is a very radically different way of building hardware, and for established hardware companies who already have a well-established flow and things like that, it's hard to penetrate with Chisel right away. There are some new projects that are starting at these big companies who also use Chisel. So I think those folks, we're engaging at that level. But for folks who have a more like a traditional way of building chips, we work with them at the Verilog level. So they're engaged with our web products. So they would come configure their cores that they would use in their products. And we're building some chip templates the kind of the generic form of chips, which are very configurable with certain companies. So you'll start seeing these startups using our services, building chips.
So microprocessor development is obviously a lot more complicated with the side channel and the giants are struggling with this, right? Is that something you care about?
I'm sorry, microprocessors? Oh, I love that question, by the way. So, right. So the question is, what are we doing really? What do I think about side channel attacks and how are you going about it, right? So side channel attacks, you can consider that a bug, but it's also a feature. Oh, I didn't know we had a screensaver. It's a bug and a feature of an out-of-order processor, of the underlying fundamental architecture, of microarchitecture of how we execute code. And it's a big problem. It's a hard problem. How do we still get all this performance while not leaving all these breadcrumbs? And the really cool thing about RISC-V is that we have a forum where everyone can work together to go solve this problem. We're not limited by Intel. We're not limited by ARM. I mean, they have a lot of money, but they only have so many people working on the problem. I really think RISC-V, the really cool feature about it is everyone speaks the same language and everyone can contribute ideas that work. So this is a time where we have to declare emergency as a computer architecture community to go work on this together. But we can't work on a proprietary instruction set architecture. That's why a lot of people around the world who are world-class experts on this topic are coming to the RISC-V Foundation to work on this together. So I believe RISC-V will solve, will mitigate the problem better than anyone else. And to kind of prove that point, there's this gnarly subject in microprocessors. It's called memory models. It's about, it's kind of reasoning about all the loads and stores and orderings and how other processors look at it. I mean, it's a very complicated mathematical problem. In the RISC-V Foundation, at the very early stage, most of the times Intel and x86 was an afterthought. They built some hardware and they tried to formalize what they built. And RISC-V, since it was an open ISA, all the world experts on memory model came to the RISC-V Foundation, and we wrote specifications, we wrote formal models, we checked them against each other, and all that. So that is the proof of why open ISAs have a brighter future than others. So welcome you to come to the RISC-V Foundation as well to work on it. Any other questions? Well, with that, I hope you can go, convince and tell your friends that SiFive is a very exciting company. Thank you very much.